Yeah, okay, appreciate that. All right, everybody has seen this morning. Does anybody need me to use the microphone? Yes, no?
Yes.
Yes, okay.
Is that better?
Thank you. Okay, well, everybody has seen the FSX spectrograph this morning. Basically what I, see this one, I didn't want to use it. Everybody's seen that. I have one that does 2 channels simultaneously, and I use them to look at Jupiter in right circular and left circular polarization at the same time, which, as we will see, can be really handy. There's why. We want to see what's there. First off, we've completely removed Faraday bands most of the time, except when it doesn't. But the question is, do modulation lanes appear the same? Do N events appear the same in both polarizations? Does solar appear the same? And you'd think it would, but once in a great while it doesn't. And why should Nan say have all the fun? Why not? There's the challenges we had. We had to have correlated samples or the data is kind of meaningless. You're going to use a dual polarization spectrograph. Fine, well, the devil's in the details. The question is, how do we do that? We needed a wide bandwidth too. It's not much use to look at 15 to 30 megahertz with a single wire half wavelength dipole. So we looked at TFDs, TP antennas, helixes, log periodics, and how to steer the beam. And TFD won out, and how to steer the beam is not that complex, but you don't just tilt it over either. How to generate LCP and RCP. I'd like to thank you for going over all that in your talk, because now I have to. It's actually pretty easy. It's not that bad. And then how do we process all that dual polarization? And again, Jim Sky made mods to RSS so that I could display both channels at the same time instead of having a fast spectrograph off the top and a slower one across the bottom. I have 2 fast ones, one for RCP and one for LCP.
Or 2 slow ones.
Or 2 slow ones, yeah. It can go either way. Exactly. And there's the DPS in all its glory behind some coax. And there's the block diagram, which, as you can see, is pretty much just 2. There's an FSX, there's an FSX, and there's just a common PIC and DDS in the middle between the 2. And everything just gets split between the 2 sides. There's what it looks like inside the box. Remember, Dick mentioned a hybrid ring. Well, there is a 10.7 megahertz hybrid ring. It's about the size of a spare tire. And that's a narrow bandwidth ring, and it works absolutely beautifully. It works well. Unfortunately, you can't have any other receivers hung off of RCP and LCP when you do that. There's its replacement. That's a little wideband hybrid from one of the microwave companies. I can't remember which right now. And how those work, I don't know. Don't even ask. Magic. There's some more IF strips. Dick mentioned that most of the spectrographs are running 30 kilohertz bandwidth. Here are some that are 7.5, 15, and 60. The DPS main unit has 30 kilohertz wide strips in it, but I've been using 60 for Jupiter, 30 for solar, and during the High Juno experiment, how many of you participated in that? Anybody? Anybody even know what I'm talking about? Holy cow. Okay, well, never mind. I used 7.5 kilohertz for that one. Same diagram we just saw one talk ago. And the DPS just runs off both these multi-couplers, and it gets LCP and RCP. And there's the RSS software that Jim so kindly wrote. And there's not much more to say about that. You said it all, Jim. Except it's RCP on the top and LCP on the bottom. Other than that, it's the same thing. And how do we generate it? I'm not going to take too long on this, because if you do get the proceedings, there's a lot of notes that are underneath the slides on this that are in the PDFs, and it does go through a pretty good explanation. If you follow the signals and the delays as you feed them in left and right to this ring, you will see how they either cancel out or reinforce each other, depending on whether your incident wave is rotating counterclockwise or clockwise. And I'm here to second Dick's motion. I don't care what you do. Do not label anything until you look at IOB. And I'll leave it at that. Yeah, I too thought I knew what I was talking about. Yeah. And then it worked, and then it didn't, and then it did again, and no, just hook it all up, watch IOB, there's your answer. It's so much simpler and painless. There's a TFD array I've been telling several of you about. It's 2 squares of those 30-foot TFDs that I have set out besides the dorms over here. And there's what it looks like, and most of you have already walked by and seen it in real life, so this slide ought to be pretty obvious. There's just how it's, goes to the observatory in that fashion. And here's an example of how to get RCP and LCP out of a square array. Basically, you're just blowing up a cross into 2 sides. Or you can think of a cross as this collapsed. You collapse the vertical ones, collapse the horizontal ones, and you end up with a cross. And it all works out the same way. But then you have 2 squares. Then you got to start worrying about the details. There's an SWR sweep of 1 element. Some of you actually saw this last night. Let's skip over most of this construction since everybody's actually seen one. Oh, somebody last night asked what's inside the bellum. There it is. It's a little mini circuits, surface mount 16-to-1 transformer. There's just one of my junction boxes that join all the elements together. One of 3 boxes out there. Raised area beam steering, something dear to everybody's heart. There's the diagram from the Jove antenna manual. Again, showing how it's really important to get the hot lead to the same side of the array. For a single frequency antenna, you can work in phase delay. For a wideband antenna, thou shalt not work in phase delay. Thou shalt use time delay, because time delay is independent of wavelength. And as your frequency changes, of course your wavelength changes, speed of light remains constant. So use time delay, and that's what we're going to show here. We'll probably skip right to that one. As your incident wave comes in from above here, it's going to hit this element, then it's going to hit this one, then it's going to hit this one, then it's going to hit this one. And as you sum all these, you need to add some delays here so that when they're all summed, there's no delay at this final combiner when the incident radiation is coming from the direction you want it to come from. One way to, I don't know, maybe it will help you, maybe it won't. One thing that helped me was that to realize whether the wave is traveling through space or whether the wave is traveling through coax doesn't make a difference. It's all the same. And what we want to do is pick off that wave signal at these points in space. But this point in space right here, well, we need to add some coax between this feed line here, this black feed line, and there's the additional coax, substituting for this amount of space that doesn't happen to exist in our array. I'm not going to go too much further because we could really bog down in that and spend about 45 minutes talking just about time delays. But suffice to say, we use time delays, and that does steer the beam over in one direction or another. The 2 square arrays are really 2 subunits. One is made up of all the east-west wires, Another one's made up of all the north-south wires. And there's what it looks like, pretty much. And these go into, the blue ones go into one of the multi-couplers, the yellow ones go into the other multi-couplers, and that's the 2 feeds that go into the hybrid to produce RCP and LCP. But we got to figure out, wait a minute, when we beam steer, what happens to the RCP and LCP response? And the way you do this, you figure it. This is just an antenna pattern, not an EasyNet. Most of you have seen this. Some of you may not have seen this type of representation. It's the same thing as this, just plotted in a rectangular plot instead of a polar plot. And same thing here again. What we're looking at here is the response broadside to the wires, and the response in the plane of, which is another way of saying off the ends of the wires. So you're both elevation plots, one's just 90 degrees to the other. And when you plot that, here's another type of plot some of you may or may not have seen. This is just a 3D plot of the TFD elements response pattern. We need to know what these are going to do when they're put together. And the way you do that is figure out what a group of isotropic radiators does when they're put together and multiply it by what that does. And that gets you the total response for 4 of these elements. Then you've got to repeat the same process for the other 4 elements and then figure out what that does when you put them together inside the hybrid. Yay, fun stuff. Took a while to figure out, but it all works out. Let's see, what are we looking at here? Here's the isotropic radiators in the north-south direction and the east-west direction. We did it at 3 different frequencies since we are looking at a wide bandwidth. We're not just looking at 20.1. We're looking at everything from 16 to 32, so we need to know what the antenna is doing everywhere in between. Well, I'm not going to do it every 10 kilohertz, but figure every 8 megahertz, close enough, good enough. There's the real dipole beams at those frequencies for the 2 different areas, the blue area and the yellow area, for lack of a better term. And what do we got here? This is all 8 elements put together. There is the final half power beam width at those frequencies. Not too shabby, really. No, it works pretty darn good. So where are we at this point? Well, we know what the DPS does. It looks at a wide bandwidth in 2 different polarizations. We know how to generate RCP and LCP, kind of, glossing over a lot of technicalities. We know how to steer the beam. We're going to use time delays. And we know the responses of the yellow and blue areas. There they are, right there. Now, we're feeding those responses into a hybrid to generate RCP and LCP. And the question is, what happens when we steer that? Does that screw us up? Does the hybrid still produce RCP and LCP reliably, or what does it do? Well, there's what it does. And this picture probably is going to need a little bit of explanation. This is looking up at the sky. East-west, going left and right, north-south here. Zenith is at 0, right across the middle here. This red track is the track of Jupiter at some point during the last, there it is, 06 January 2014. What these contour lines represent are the gain difference at, say, this point right there. That right there means that there was a 1 dB gain difference between the north-south wires and the east-west wires. Which means when we feed those 2 signals into the hybrid, what we're getting out is pretty much true RCP and LCP, but with that gain difference, there's some iffiness there. We can't go work backwards and say, well, the source signal was pure RCP and LCP because of this gain difference. And these 2 are just at 2 different frequencies. So anyway, long story short, at zenith or near to zenith, we got nothing to worry about. This big X-shaped area means everything's working beautifully. It pretty much covers the whole half power beam width. We're good to go as long as Jupiter is within the 3 dB well, beam width. Well, we start beam steering though, and oops, weird things start to happen. And it starts to happen worse and worse. And if you try to beam steer way over here, no can do. And that's why earlier in the year, when I had the array steered way over, we still saw Faraday bands, even though theoretically everything was steered, but you've got such a difference in response between the broadside of the TFD and off the ends of the TFD. Well, this is what you get instead of using an array of 77 TV antennas. And there's all the math behind it for those of you who are inevitably going to ask. Don't worry, there won't be a test. So, here, the DPS system, some general specs here. We can pretty much reliably beam steer up to 30 degrees. We think the directivity is about 14 dBIC. We're not 100% sure on that. EasyNet and Real World don't seem to agree too well. However, the results we got last year, it's working really well, so good enough. Bandwidth we talked about, dynamic range is the same as FSX, same as the noise figure. 2,000 samples per second times two sides, that's just more FSX is 12-bit, 2 to 500 channel. Well, I guess it's 200 to 512 now, isn't it, Jim? 2 to 512. Right. Yeah, exactly. It's going to make such a difference. And the sweep rate is just a function of the number of channels because the number of channels per second is fixed. So if we want to display 500 channels, our sweep rate gets lower. That's all. And that's the same for all FSXs. Oh, here's some observations. This you've seen, except now here's the DPS stuff up here, and here's the DPS display here. We actually used the DPS display here to determine where to tune the TWB here so that we could image S-bursts in high detail. These two receivers work hand in hand during an IOB event really well, and just superb. What do we got here? Here's some IOA back from December. Yeah, here's one example I wanted to show. Lots of Faraday banding in here, but Jupiter was 50 degrees off axis. Well, with the difference in response patterns between the two directions of the TFDs, there you go. No matter what you do, you can't escape. And the rest are just some really neat reasons for a DPS. Here's some IOAC, and yep, there it is. There's the slide I wanted. Right there between IOA and IOC, a lot of times you get emission at the same time from both sources. But how do you know which one came from the IOA source in the northern hemisphere and which one came from the southern hemisphere, the IOC source? Polarization. And there you go. This right here, this RCP, this was IOA. But down here, LCP, that was IOC. And it was right in between the two sources there. This is the prime reason for looking at both polarizations. And there's some more, some of this is just really fascinating. Haven't seen too much. I didn't cherry pick the data for any reason. There it is. Some leopard prints. Remember that one, Wes? Those leopard prints? That was when you were at the observatory, I think. Here's some possible IOD. This happened just above the IOB region of the phase plane, and we think this down here might actually be IOD because IOB shouldn't be emitting in LCP, and it's not emitting in RCP, so the only other choice is IOD.
Dave?
Yep.
Can you send me that plot?
Which? This?
No, next one.
This one here?
Yeah. I see something similar to that with the LWA.
Yeah, I thought I did actually. We talked about this before, I thought. But, yeah, send it again. Or the first time, I don't remember, to be honest with you, 100%. Who knows? But by all means, yeah, definitely. Where was I here? IOB, RCP dominant, yeah, blah, blah, blah. Here's just some Oh, I mentioned early on, I wanted to investigate, do the modulation lanes happen at the same time? In other words, if we looked at the modulation lane in RCP, would it be 180 degrees out over here? In other words, would it be bright in left and dim in right, and then vice versa? Would they be interleaved, or would they happen at the same time? And apparently they do, because right along this red line is a nice peak between the modulation lanes, and it's showing the same thing. Which, in this case, makes a lot of sense, because all this is showing you is that this right circular polarization isn't perfectly right-hand circular polarized. There's a little bit of other stuff mixed in there.
Yeah. As far as I know, but I'm not sure, I think what you see here is acoustics that are due by is the ionospheric scintillation. There are big disturbances in the ionosphere of the Earth that are making acoustics. So most of the details that you are here may be added simply by the ionosphere and not from the
Yes, you're anticipating the rest of my comments. Exactly. We're trying to determine right now whether these are ionospheric or Jovian to begin with. And I don't know, so I want to get with you after the talk. It seems to me, it's interesting that they're sloped positive here and negative here and kind of vertical here. I don't know what happened here. I don't know if Jupiter passed zenith right then. I don't think it did, but anyway, there's some neat stuff. There's that, my favorite IOB one that everybody's got. That's just a really nice one. Some more observations, same stuff. What am I? Oh, here's an example. When I was seeing this, right there's some S bursts, and I would tune the TWB to that frequency, about 27 megahertz, and record, hit the record button, and that's how we did that. And here is a really weird one. This might actually be an IOD-N event. We've got RCP here, there's where Jupiter was during this observation. We've got this N event right here, this little fuzzy line, not WWV or whatever that is right there, but that fuzzy line right there. Why that's LCP and why that's there, I got no clue whatsoever, guys.
Probably IOD.
Yeah, is that an N event? Does IOD do N events? I'd like to think it is, because that's a first, for me anyway. And that's it, guys. Who else has questions? Anybody? Go ahead.
On the spectrograph, the one right after the geoprint one, the one that's geoprint, can you go down?
Oh, this one?
Yeah.
Yep.
So right around the frequency of what looks like the radio waves would be, why does it look like it's only like on one side and not the other? Is it being disrupted by Jupiter's radio waves? I didn't think it was strong enough to do that.
Okay, I'm not sure I understand the question.
Just about 18 megahertz.
Yeah.
Why is it being disrupted by Jupiter?
Oh, it's not. That's just plain old coincidence.
Okay.
That transmitter just started being able to be received around that time. Has absolutely nothing to do with Jupiter. Just random chance. But
your spectrum that you're covering here includes the amateur 17 and 15 meter bands.
Yeah.
What are the artifacts of that kind of activity
Right there.
appear like?
just like that.
Okay.
Just like that. Anybody else? Go ahead.
How do you do your variable delays to steer the array?
That's what I skipped over so we could get out of here on time.
I'll talk to you.
I would be happy to go into that in great detail.
Okay.
Just a short question. Would it be possible to record the data in linear polarization and then do the transformation into circular polarization software afterwards? This is how it's done for the AWS.
Right, but we are not recording this data at high speed. This is recorded at 6 samples per second.
It would be done in real time just after digitization. That's not easy.
Right, we're just, so I don't think so. Yes, Francisco.
Yeah, that's the same thing that we can do. I think we talk about the same. When you are combining the same from the full set of dipoles, and it's a little bit off from the central beams, you are combining things as you said, with different attenuations. So, right, the right thing would be to digitize the signal right there, but that requires to digitize signal
Like the LWA does.
very, very fast. Right, and then you can introduce more the 1.6 the digital.
Well, yeah, then you can get your full set of S parameters out of it and you're done. If I had $10 million, I'd buy an LWA. Or 100.
That's really fast. You know, 32 megahertz, you would have digitized some.
At least 60, 70 megahertz at least. Anybody else? All right, that's it.
Thanks, Mike.
Let's go take answers.